Okay, so we were actually discussing, we have just started discussing actually on discriminant function for the multivariate Gaussian density. So we have seen the equation for maybe the Gaussian density. Okay, equation here. And then okay, so we have seen how we can actually define a discriminant function, because this function is going to be used for maybe making a decision on whether a given x is actually okay corresponding to okay w1 w2 or say w3 etc. Okay, so just wait a moment. Okay. Okay. Okay, anyway, okay, so so that is actually why we are actually maybe defining okay or discussing on this discriminant function. So we, that will be clear maybe when we discuss an example okay later. So then so that means this probability is actually we are assuming that that is actually defined by this particular distribution or the density function, and then we can substitute okay this particular value okay here okay in this particular equation for j of x, and so that will result in an equation like this one. Okay, just substituting and rearranging okay maybe say terms. And then we have seen we will be seeing different cases. Okay, so that means here the most crucial part is actually the covariance matrix, as we have discussed yesterday. So we are seeing with three different cases. Okay, so in one case we are assuming that so that is this covariance matrix is actually okay say sigma square I. Okay, so we are assuming that the features are actually okay independent, statistically independent. So that means the off diagonal elements are going to be zero. So we'll have only the values in the covariance matrix only in the main diagonal. Okay, and so and we are again we are assuming that each feature has got to the same variance. Okay, so that this is going to be a very very maybe rare situation most probably, because in when you consider any random maybe any real life situation, there can be situations like this in some cases, but generally it may not be the case. Okay, we will have any arbitrary covariance matrix okay for a given problem, so that we will see later. Okay, so so then now if you look into this particular equation, that is our okay this equation, we can see that this particular term okay is nothing but okay it is going to be a constant. Okay, and similarly this term is also going to be constant, because we are actually taking this for different okay classes w1 w2 w3 etc wwc. So that means here also we are assuming that for each of the w, so that means we are assuming that suppose here we have a the data set of this kind okay as we have just discussed. Okay, and so, just wait a moment. Okay, I will make some arrangements because I am actually not able to use my pen, so just wait a moment. Okay. Okay, so that is not working anyway. Okay, so we will continue with this one. uh, so that means assume that we are having okay say different rows here okay maybe in a data set, and assuming that a few of these okay so rows okay corresponding to w1 okay, and another okay set actually corresponding to w2, and another okay subset corresponding to w3 etc. Okay, so that way we have a g1 of x, g2 of x, and g3 of x. Okay, so in this particular case we know that so this sigma is going to be sigma square into I okay of this form. So that means this term is also maybe not significant for us, because that is going to be same for g1 of x, g2 of x, and g3 of x. So we can actually ignore these two terms. Okay, and we now we will get an equation of this kind. Okay, So this is actually the Euclidean norm, okay, x minus, because x is a vector, okay, of d dimension, and mu I is also a vector, okay, of maybe, okay, of d dimension, okay. So that means here we'll be considering, so for example, when we consider g1 of x, we will consider only those points corresponding to, okay, the rows corresponding to w1, okay, in the given maybe data set. So correspondingly, we will find the mean vector, okay, etc., etc. Okay, then similarly, we have the prior probability also. Okay, so that is actually what is this particular term. Okay, so this is nothing but okay, the this particular term, okay, that we have taken. Okay, and so that is actually how the discriminant function will look like. So that means you are given with an x vector, which is a vector that you have to maybe check whether that belongs to w1, w2, or w3, and then this mu I we can calculate from this particular table. Okay, and sigma square we can calculate, and the prior probability we are assuming that is also, okay, either given or we calculate from this given, okay, data, whatever it is. So if you look into maybe this particular, okay, discriminant function, okay, we can say that so here there are two terms. One is actually the this particular term, okay, and here we are having maybe, okay, probability of maybe say the prior probability. Okay, so when you look into maybe say this equation, we can say that it favors actually, okay, a priori, okay, more likely category. So because whichever is having, okay, the maybe so having the large value for a prior probability, okay, then that will have an impact, okay, because we are actually adding that value to this term, and we are taking and we know that what is a decision that we are taking, that is we are actually considering whether g1, okay, g2, and g3. So whichever is actually larger, okay, we will assign that particular, okay, w. Okay, so that means we can say that it favors an a priori more likely category. So that is the significance of this term. Okay, then suppose we expand this equation. Okay, so that means we are this equation, suppose we expand it. Okay, and then we will get an equation of this kind. Okay, that is okay, x into x transpose, okay, sorry, minus 2 into, okay, so we are doing this multiplication. And if you look into this particular equation also, okay, we have x transpose into x. Okay, so that term is also going to be, okay, insignificant, okay, when for our maybe say decision making, because that is going to be a constant for whether g1 of x, g2 of x, or g3 of x, because it is the same feature vector and it's a transpose. Okay, so that means that term we can actually ignore, okay, because that is going to be the same for g1 of x, g2 of x, and g3 of x. So that is one another simplification we can actually make it. So by considering that particular simplification, we can, so that means we can disregard this particular constant, okay, and then we will get an equation of this kind. Suppose we rearrange or we express g of x in this particular form, where this term, okay, that is a wi transpose, is nothing but, okay, this particular term. So this is nothing but this is obtained from this equation, okay, just to replacing a few, okay, representing this particular term with a wi, okay, and maybe this particular term, which is also going to be, okay, the remaining term in this equation. So that let us represent that as wi0. Okay, so but why we are actually making expressing this equation in this form is this has got a very interesting maybe representation, and that is going to be maybe used maybe throughout our maybe discussion of this course, and that is a very maybe well maybe accepted and maybe well I mean, or we can say that this expression is going to be a basis for many pattern recognition, maybe say techniques that we will discuss. So this particular equation, okay, of this form, that is g of x is equal to w transpose x plus w0, is we call it as a linear discriminant. Okay, so that is a case. So linear discriminant, because this is actually linear in terms of the x vector. Okay, so the feature vector is actually not maybe quadratic or maybe more in maybe degree. So it is simply a linear function in X. Okay, so that's why we call it as a linear discriminant. Okay, so that is, it's very interesting actually. So you can actually okay, we have already defined the term wi and okay, wi0. Okay, so keep in mind that this bold w is going to be okay. That is a vector multiplication. Okay, because it is a mu I divided by sigma square. Okay, because you are actually multiplying the transpose with the x vector, and this wi0 is a it is not a vector. It's a maybe a scalar quantity. Okay, so that actually maybe I mean the of this particular term, and that we sometimes we refer to as a bias term. Okay, and otherwise sometimes we call it as a threshold. Okay, so threshold or okay, biases, these are the two terminologies. Okay, maybe usually I mean maybe used to represent that particular quantity. So that is a bias and or bias threshold. So that is a linear discriminant. And so when we use this linear discriminant function, okay, then we that linear discriminant function, suppose we use a linear discriminant function to make a classification, then we call it as a linear machine. Okay, so that particular system which is used to make a decision based on linear discriminant functions is actually called a linear machine. So that is a terminology that is used. Okay, and then so we can have a multiple decision regions. We have seen what is a decision region corresponding to R1, R2, R3. So those corresponding to W1, W2, etc. Okay. Okay. So that means when you consider a decision surface, okay, when you consider a decision surface, just wait a moment. Anyway, it is not okay. Anyway, so here assume that we are having a decision region, say for example R1, okay, and suppose we are having a okay, say region say R2, okay, so this is R1 and this is R2. So we have this particular region. Okay, so that is the region maybe okay that actually defines the boundary between okay R1 and R2. Okay, so that is actually the decision boundary. Okay, and that is actually set by, we are assuming that the decision boundary G of x is equal to Gj of x. Okay, so this is corresponding to okay gi or g1 maybe in this case. Okay, it is a, we are using ga and gj representation. Okay, so that is that particular what is actually a decision boundary looks like, and what is the property that is actually maybe that we can actually assume at that particular decision boundary, because there the values are going to be same. Okay, so that is a case. So that is g of x is equal to gj of x. Okay, uh, fine. So if that is the case, suppose we substitute okay this g of x, okay, and corresponding gj of x into this equation. Okay, then we can make a rearrangement of this form. Okay, that is w transpose into x minus x0 is equal to 0. So we can maybe we can define the decision boundary like this one. Okay, so this is a two class classification case that we are just discussing. Maybe but this can be extended to, say for example we are having a region 3. Suppose the region 3 is actually coming here, then the same thing we can actually say that in this particular decision boundary we have g2 of x is equal to say g3 of x. So like that we can have maybe say we can find out the decision boundaries okay accordingly. So that is actually the case. Okay, so this is the equation, and if you substitute this
How X0 came?
hello.
And how X0 came? W transport into X minus X0.
This one, so you can see that these are actually the terms already defined at the bottom. Okay, so this x0 is actually nothing but this term that you will get from maybe by substituting this. Okay, you got it.
Okay, sir. Okay, sir.
Okay, so this is actually nothing but you are applying this equation, and you are applying GJ of x, GA of x and GJ of x. So that means substituting the corresponding values of Wi, Wj, and Wi0 and Wj0. Okay, and then maybe we are just rewriting of this form because this is a decision boundary form. We are assuming that is something equal to 0. So that is the way we define decision boundary, because G of x is equal to 0 is a decision boundary. Okay, so here it is of this form, but there are W vector. Okay, so that W is actually nothing but the difference in the mean vector, okay, of mu I and mu j, because here now we have it involves actually two decision regions. Okay, one corresponding to G1 and another corresponding to or Gi and Gj, or Ri and Rj, and all the remaining terms, okay, that we will get by substituting this one. We assume that that corresponds to x0, which is this particular x0. Okay, maybe if you are interested, you can go and maybe work out. Anyway, you will get this equation. So we are not going to that way of maybe say maybe deriving it or anything, but I think it is straight away we will get just rearranging the terms and maybe making of this form. So this is a way how we can actually define a decision boundary, okay, of a linear discriminant function. Okay, and so now if you look into this particular equation, there are we have two terms defined, W and x0. Okay, so when you consider, okay, to a two class problem, okay, assume that here we are considering two classes. So there are two mean vectors. We have a mu I and mu j. Okay, so there is an interesting some properties that we can actually maybe we'll get an idea maybe by looking into this particular cases. So some of the properties of this decision boundary that we have just described is actually, okay, so this decision boundary actually passes through maybe this this x0. Okay, so x0 is actually a point, we can say that through which the decision boundary will pass through. So that is one property. Okay, and that the and I think we have already seen a terminology called a hyperplane. Okay, so that is a hyperplane is nothing but so maybe a decision boundary, okay, that is of maybe a general n dimensional case. Okay, so that means we can have actually hyperplanes in 2 dimension, okay, 3 dimension. Suppose our data the is of d dimension. So the d dimension data can be of your given data can be of a 2 dimension, 3 dimension, 10 dimension, 20 dimensions, 100 dimension, 1,000 dimension, like that. So we generally call a decision boundary we define in any of these d-dimension spaces a hyperplane. Okay, that's a general terminology used in maybe in the machine learning context or pattern classification context. So we assume that decision boundary, okay, maybe a hyperplane actually passes through x and it is orthogonal to the line linking the mean value. So that is we have in this case mu I and mu j. There are two classes. Okay, so that is another interesting property. So the point is that maybe the W, okay, so W is a it's a vector. Okay, so that is actually defined by in this way, difference between the mean vectors. So if you look in there, so for example, let us assume that the hyperplane is a straight line. Okay, so this straight line can have actually different orientation. Okay, and similarly the straight line can be maybe suppose so that straight line can go through the origin. Okay, if it is a 2 dimensional, or it can go through maybe a point that is cutting the x-axis or the y-axis. So that means corresponding to x1 dimension, or sorry, x1 feature and x2 feature, whatever it is. But the interesting point is that so that is going to be orthogonal to the mean that is connecting. Okay, so the two mean vectors. So that means we can say that this actually decides the orientation. Okay, maybe the orientation of that hyperplane is actually maybe you can have that is decided, or it is influenced by the W vector, and we call it as it passes through x0. So that means how much distance or offset from the origin. So because this is something similar to, you can say that equation of a straight line you have studied, y is equal to mx plus z kind of thing. So where the slope of the line actually determines maybe the orientation or the direction of the maybe the line and maybe the C, we call it as a y-intercept. Okay, so that actually decides how much it is from the origin. So it's similar. This is our discussion is actually a very generalized one, but that equation of a straight line that we have discussed is a very specific case. We will come to this point maybe later also, but these are two important properties. And then now if we can look into this particular equation, there are very interesting things. So for example, what is going to be the case when the prior probabilities are actually same? Okay, so that means that is probability for class 1 and class 2, or the w1 and w2, or wi and wj are same, then you can say that this term will vanish. Okay, so that is a case. Okay, so that will vanish, and now what we will get is the x0 is going to be mu I plus mu j divided by 2. So that means we can say that the x0 is nothing but exactly passing through the middle of the line connecting the two feature vectors. So that means the mu I and say mu j. So that is one property. Okay, and suppose we have a probability of, okay, the prior probabilities are different. Okay, then there can be interesting thing. Okay, whether wi, probability of wi is actually greater than probability of wj, or probability of wj is actually greater than probability of w. So there are different possibilities. Okay, so anyway, the interesting thing is that okay, if they are different, okay, then x0, so that means we know that it is a point through which the hyperplane will pass. Okay, so you can say that that will shift away from the most likely category. Okay, because that is going to accommodate maybe maximum number of maybe say points in that particular category. So that also we will see pictorially. Then if it is sigma is very small, then okay, maybe this is not, it is insensitive. Anyway, as in that case we'll have the previous equation that we have just discussed will be the one. So these are some of the points. And now we will see, this is a typical example, okay, which we have actually just discussed. Suppose we have two distributions, so that means for the two classes, okay, w1 and w2, okay, and assume that we have a probability of w1, the prior probability for first class is 0.7, and that of w2 is 0.3. Okay, so we can say that we have actually say this is corresponding to the mu1, okay, and this corresponds to maybe the mu2. Okay, the two mean vectors that we can calculate or we can define. Okay, and then this dotted maybe black line, that actually represents our decision boundary. Okay, because in this particular case, okay, because we are assuming that is a single feature only, so we can say that a point is going to be the hyperplane. Okay, in that particular case, because all the points belong less than a particular x belongs to one category, and all the points belong to right side belongs to maybe the other category. So that is why we are saying that we have a region 1 and region 2. So that is defined by maybe this particular point. Okay, this point. So that is we can say that now we will say that all these points are belong to R1 region, and all this belongs to R2 region. Okay, maybe up to whatever value this takes. Okay, but suppose that if the prior probabilities are maybe having this particular values, so that means we have a 0.9, okay, in one class, and okay, 0.1 in another class. We can say that this line, this, okay, this will shift it towards a more, okay, away from that particular point. So that means we have the region one is actually enlarged, because most of the points will be maybe corresponding to the region 1, and we have R2 is actually reduced. So that is actually because probability of w1 will have a impact on g I of x, so g1 of x, so that your values will be maybe correspondingly the decision will be more for preferring w1. So that is actually one case. And suppose when you have a two dimension, okay, or a three dimensional of kind, so we can see that suppose we are having a one distribution of this kind of maybe ashen color, and another one is a red in color. Okay, so and we have seen that the projection, okay, we can have okay, so we say we are saying that 0.8 and 0.2, okay, they are the two probabilities. Okay, and in that case suppose we assume that So that is this is a decision boundary, okay, the with respect to the projection. And so when you're having say 0.99, suppose in another case, and 0.01, okay, then we can say that that shifts more to this, so that the R2 is actually, that red region is actually very small, and the majority are actually going to be predicted as maybe W1. So this is maybe in a higher dimension. That's the only thing. So this is similar to exactly whatever we have seen in this particular case, but this is actually when you are having a feature vector, okay, maybe in 2 dimension, okay, or 3 dimension, like that. So that is a case. And this is a maybe exactly in 3 dimension, okay, because when you consider in 2 dimension, in your hyperplane is actually going to be a straight line, okay, but when it comes to a 3 dimension, okay, your hyperplane is going to be a plane, okay. So that is why. And keep in mind that whenever we have actually maybe the representation is actually spherical, okay, we are representing that I mean the, because we have seen that whenever a Gaussian distribution, okay, we can actually represent it as a hyper ellipsoid, okay. So that is a general term that we have seen yesterday, okay. So we look at the points of constant probability, and so if we plot, you will get a of that different shape. So if it is in a 3 dimensional, now we'll have a, okay, this sort of representation, okay. And maybe in 4 dimension may not be, will not be able to represent maybe in our system, but similarly it is going to be maybe of similar kind, maybe. So that's why it is called a hyperplane, hyper ellipsoid, or hyper, okay, so that representing a very high dimension, okay. But whatever analysis or theory that we actually derive or maybe have for the lower dimensions, okay, are exactly applicable to maybe say higher dimension also, okay. So that is a case. So here also we can see that a 0.8 and 0.2 in this case, and this is a 0.09 and a 0.01, maybe in a your vector, okay, the x vector is going to be maybe 3 dimension, okay. So similarly the case. So that is a how this will look like geometrically, okay. Then if you look into maybe another very specific case, okay, suppose we are having the the p of w are actually same, that is prior probabilities are same, okay. So then we can say that this term, okay, because our linear discriminant function is of this kind, okay, and this term we can just ignore, okay, because they are going to be the same value whether it is for w1 or w2. So then your our say discriminant function will be of this kind, minus x, the x minus mu I square, okay. So here we can see that so here we actually look for g of x maybe greater than, okay, which is larger, okay, we are saying. So in order to have larger, okay, when you look into this particular case, okay, here you are having an x vector and a mu vector. So you calculate, okay, the distance of your feature vector to mean vectors, that is for mu I, mu j, or say for example mu1, mu2, etc., okay, and to which mean vector your x vector is actually closer, okay, we assign that particular class level, okay. So because this is a -1, okay, so that means larger values of g of x corresponding to, okay, they say this diamond, this value will be minimum. So that means the a feature vector must be maybe classified as a class level, say for which the feature vector is actually closest to the corresponding maybe mean vector. So that is actually called a special minimum distance classifier, okay. So that is maybe we have seen such a maybe figure, or say the architecture of a representation for a maybe a classification system with multiple discriminant functions here, okay. So we have seen that we are considering a maximum of the output produced by each of the discriminant function. So that is a way, okay, we have actually have this particular case here. So it's a special case, okay. So these are some of the cases that we can actually maybe define. So this is we have started with where sigma, we have assumed that okay, it is same statistical independence and etc, etc, okay. But maybe we'll go to another case, okay. Maybe it's a case 2, we are assuming that the sigma I. So that means the covariance metrics are actually same for okay all the classes. Okay. So that means there is no statistical independence. So that means there will be some covariance existing between feature x1 and feature x2, feature x1 and feature x4 and feature x2 and x6, etc., etc. But we assume that that matrices are actually same. Okay, for all the. So that means they are having the same covariances for all the different classes. Okay, so that is a another possible maybe analysis. Okay, another possible case that can come across. And yesterday we have seen that this covariance matrix actually determines maybe the shape of maybe how the points will be okay falling. Okay, if we actually plot that the plot for the constant density cases. So that is the case. So here we have the same equation, that is a general equation for a discriminant function using normal density, the same equation. So we will start with this same equation, and then now we will discuss on this particular case too. So here also we have seen that there are different clusters of points, and we call it as a hyperellipsoid general shape. Okay, and we are assuming that they are going to have the same size. Okay, because we have actually maybe say the same maybe the mu vector. Okay, for all the cases. So, but here we will see how maybe we can simplify how the linear discriminant function will look like, etc. So here also we can say that this term we can ignore because that is going to be a constant, and this can also be ignored because even though say we have a covariance, we are assuming that the covariance matrix is exactly same for different classes. So that means again there is no point in there is no difference in the covariance matrices. So that means we can ignore these two. Okay, and so we will get to the previous equation. Okay, similar to that we have seen for case one. So and now if you expand this one, so that means this term. Okay, then we can ignore okay the quadratic term, because that here also we'll have that x transpose into x will come. So that is going to be same for all the cases. So then we will get the linear discriminant of this particular form. Okay, and so here but there is a difference. Okay, because we have a the sigma is actually not exactly sigma square I. So like we have seen in the previous case. Okay, but here we have that okay sigma inverse okay is actually kept okay as such here. Okay, similarly here also we have the mu is not simply okay maybe as in the previous, but there is a multiplication factor that inverse of the this covariance matrix comes into picture here. Okay, so that is by expanding this one. So that is a difference. Okay, when you consider okay maybe the linear discriminant, but here also you can we can call it as a linear discriminant because the quadratic term of x is actually constant, so we can ignore. So there is no maybe higher order, just the linear maybe in x. So that is a by again we can say that this case also corresponds to a linear discriminant. Okay, and then it is the same analysis we can continue the decision boundary, that is g of x is equal to gj of x, and we will get this decision boundary, but there is a difference. Okay, when we, on the say the term w and also on x0. Okay, there's a difference because earlier it was mu I minus mu j, but now we have the covariance matrix and its inverse comes into picture here. Similarly, here also we have actually the difference comes. So that is the major difference actually comes okay when we are having maybe say the case two. Okay, so that is the case, and when we look into this particular properties, okay, similar to the earlier one, we can say that the decision hyperplane will pass through, or the decision boundary will pass through x0. But due to the this multiplication factor of okay the sigma inverse, okay, it is not orthogonal to the line linking the mean values, but it will pass through. So that means it will be at an oblique, say with respect to the line that connects the mean vectors. So that is one change, but still it is applicable. Whatever decisions that we made actually is going to be applicable here also. And again, we have to look into what will happen when prior probabilities are same and probabilities are actually maybe exactly same as maybe when they are different also, as we have just seen for the case one. Okay, so you can say that this is going to be how maybe there's a, that will look like. Okay, maybe so you can see that maybe the difference will be coming. Okay, maybe when you consider this particular. Okay, earlier it was actually vertical. Okay, orthogonal to the line connecting, but now you can see that that is at an slanting position. So that's why it is actually not perpendicular to maybe the mean corresponding to, okay, that connects actually these two cases. Otherwise it remains the same. Okay, because here also we have a exactly we can say that it is not perpendicular to the means which are connecting. Okay, so similarly the shifting occurs depending upon which maybe prior probability is actually okay larger, so in that direction it will actually prefer, okay, the decisions actually. So all this actually remains the same case. Okay, there is no additional thing here. And here we have another interesting maybe say classifier. Okay, so yesterday we have actually seen a Mahalanobis distance. Okay, so actually that was actually squared Mahalanobis distance actually. Okay, I just forgot to mention that squared, okay, term. So because it was actually r square. Okay, on the LHS side we have so that is actually called as squared Mahalanobis distance. So so here, suppose when we are having the same prior probabilities, okay, we can just ignore this term. Okay, so this is a equation that we have actually obtained. Okay, for the linear discriminant. Okay, in the previous slides. So what is remaining is actually okay this particular term. Okay, so you can see that this is actually x minus mu transpose into sigma inverse into, okay, x minus mu is actually was the Mahalanobis distance we have actually defined yesterday. Okay, so that's why it is actually called. It is actually based on the Mahalanobis distance. So it will actually it reduces to that distance. So that's why it is a special case. When we are having the prior probability same, we are having the this classifier is actually called a Mahalanobis distance classifier. So, but it remains the same. So that means you have to take the maximum. Okay, out of maybe all the g of x. So I think that is also another maybe result that we can actually maybe obtain. And finally, this is the case three. Okay, this is a case three where we assume that the sigma is actually arbitrary. So that means when you consider all the tuples corresponding to W1 and all the tuples corresponding to, okay, the data points corresponding to W2, they are having different covariance matrices considering x1, x2, x3, etc. Similarly here also it has got a different maybe say covariance matrix. So that's arbitrary. Okay, so that means it can take any shape. Okay, so so that's a complex case also. Okay, so that means the clusters can have a different shapes and sizes. Okay, and each of the cluster we know that they are going to be centered at their mean vector. So that is always maybe true, but the shapes and sizes are going to be of any kind. Okay, because we don't know how the covariances are actually going to be, okay, with for each classes. But so when you look into this equation, we cannot actually ignore this one because sigma I is going to be different for different classes. Okay, but we can still ignore this one because that is a constant. So that means we will have an equation of this kind. Okay, that is g of x is now it is not a linear discriminant, but it is going to be quadratic discriminant. That is a major difference when we are having an arbitrary, I mean the covariance matrix. Okay, and so corresponding, okay, w, okay, this is a term that is defined. Okay, w, so this is just a rearranging. Okay, nothing additional knowledge is required. And similarly we have a, okay, small w, okay, this term. Okay, and we have the offset or bias. Okay, all these are actually maybe we don't have much simplification actually possible. Okay, in this particular case. So it's a general case. Okay, and now the decision boundary is we call it as called hyperquadrics. Okay, so that is a term that we use in that case. So here it is very complicated because we set j of x is equal to gj of x. Then depending upon maybe the covariance matrix. Say for example, in some cases the covariance matrix can be the previous case. Okay, but in one or two classes. Okay, but when you consider another pair of classes, it can be different. So there are many possibilities actually can come. So accordingly, we can have a hyperplane itself, or there can be two hyperplanes we may have to. So for example, two lines you may require sometimes, or two planes you may require sometimes in order to make a decision. Or there can be hypersphere. Okay, it can be spherical in shape. The decision boundary, the hyperplane itself can be spherical in shape, can be ellipsoid in shape, can be hyperparaboloids in shape, or whatever shape can actually assume. Okay, so that is the complexity. Okay, that can involve when you are having a any arbitrary maybe say case. Okay, but maybe so we will have actually I don't know whether that shapes are actually here or not. Okay, I think we will stop today and we will continue in the next class. Okay, so thank you for listening. We'll continue the remaining. Okay,
Thank you, sir.
okay, thank you.